Welcome to module 13 of the course Ultrafast Optics and Spectroscopy. In this module, we'll go over ultrafast processes involved in transition metal complexes and biomolecules. Transition metal complexes exhibit beautiful colors which are related to their UV visible absorption spectrum. The first interpretation of the UV visible absorption spectra of transition metal complexes came with the development of the well-known ligand field theory. This ligand field theory was developed to interpret the UV visible absorption spectrum of transition metal complexes. According to this theory, 5 different electronic transitions can be involved in transition metal complexes. The first one, metal to for the first one is metal centered excitation, which is also called DD electronic transition. So, if I assume that I have a transition metal complex something like this, we have kind of a structure of, let us say this kind of structure we have, this M representing metal and L representing the ligand. What kind of structure we don't need to know immediately, but let us say I have this kind of structure. So, this is your ML5 complex, transition metal complex. In this complex or a complex something like this, we can have metal centered excitation where it is the excitation is localized in the metal only, where we can have DD transition, d orbital to d orbital transition. The DD electronic transitions are in principle Laporte forbidden in centrosymmetric environments. Laporte forbidden because Laporte, in order to have Laporte allowed transition, I need to have delta L equals not equals 0. So, it is Laporte forbidden transition. However, they are partially allowed due to vibronic and spin orbit coupling, and thus in general they exhibit lower excitation coefficients as compared to charge transfer excitation. What is charge transfer excitation? The second one is ligand to metal charge transfer. There are 2 different kinds of charge transfer we can have. We can have charge transfer from metal center to ligand center, metal to ligand. So, I have ligand, so I can have an electronic excitation from metal to ligand, or I can have electronic excitation from ligand to metal as well. So, both are charge transfer. So, charge transfer excitation is not a local excitation. It is centered in 2 different moieties. In ligand to metal charge transfer, we promote electrons from occupied ligand orbitals to the partially empty d orbitals of the metal. Ligand to metal charge transfer excited states are low lying states when at least one of the ligands is easy to oxidize and the metal is easy to reduce. Then we have another charge transfer, metal to ligand charge transfer excitation, where we promote an electron from occupied metal d orbitals to the low lying empty orbital located on the ligand. Metal to ligand charge transfer excited states are expected to be low lying ones when the metal is easy to oxidize and the ligand is easy to reduce. Then we can have intra-ligand transition. Inside the ligand, I can have, just like metal centered excitation we have discussed, similarly ligand centered excitation we can have as a local excitation. This excitation occurs in the ligand itself. Intra-ligand transition involves electronic excitation between ligand based orbital which are located on the same ligand. These orbitals has to be in the same ligand. They are usually present in the UV visible spectra of ligands without complexation with the metals. So, it is more like a ligand property. And the last one is ligand to ligand charge transfer. So, we can have a electronic excitation coming from one ligand to another ligand, and that is called ligand to ligand charge transfer. This involves orbitals located in different ligands. Due to presence of different electronic excitations which are possible in transition metal complexes, the description of the UV visible spectra of transition metal complexes are very complicated than for organic molecules. It's not like organic molecules, they are more complicated than organic molecules. However, ligand field theory coupled with different selection rules provides an excellent way, a predictive way, which enables us to predict the UV visible spectra of transition metal complexes. In addition to different vertical excitation processes, which we have discussed in the last slide, photochemical and photophysical events in transition metal complexes also involve processes which are opened up after light absorption. And these are processes very common to any system. Possible photochemical pathways are discussed in this Jablonski diagram. Here, several electronic states, including the singlet ground state, which is shown by S0, electronically excited singlet state S1, and electronically excited triplet state T1 are shown here with associated vibrational states. These are vibrational states associated with the corresponding electronic states. After Frank-Condon vertical excitation to the singlet excited state, which is S0 to S1 transition, following this transition, this is a vertical transition, following this transition, nuclear relaxation can lead to several radiative or non-radiative pathways. Radiative process involves fluorescence, which means that I can have a return from S1 to S0 by incoherent emission, and that is fluorescence. We can have phosphorescence, where I can have population transfer from T1 to S0, and we can have phosphorescence. These are the radiative processes. On the other hand, there are three important non-radiative processes are shown here: IVR, IC, and ISC. These are non-radiative processes. These are non-radiative processes. The excited molecule may relax via vibrational excitation, vibrational relaxation mediated by solvent deactivation and molecular collision to a minimum on the excited singlet potential energy surface. This process is called IVR. So, although we are exciting to this upper vibrational state, that can relax back to the ground state of the upper excited, electronically excited state through this IVR process. It may also happen that excited molecule with enough vibrational energy may reach regions of the potential energy surface, and eventually population is transferred from upper electronic states to the lower electronic states through the non-radiative population transfer. There are two different non-radiative transfers which can occur. The first one is intersystem crossing, ISC. Intersystem crossing always will be involving two different spin states. So, we are transferring population from S1 to T1. And another one is internal conversion. Internal conversion is also non-radiative process where molecule can jump from upper excited state to the lower excited state without radiation, and but we do not change the spin state. So, the primary difference between IC and ISC that we are changing the spin state in in the process of ISC, and we do not change the spin state in the process of IC. In the context of photochemistry and photophysics of transition metal complexes and all organic molecules as well, it is assumed that the fastest process occurring in the course of excited state relaxation is IVR. So, IVR is the fastest process, then I have IC, then I have ISC. This is this order, and this is the rate. Okay, how fast is going on, and this order has been accepted mostly in general photochemistry and photophysics, and that's why we can write down the rate constant like this. This is anticipated trend. This anticipated trend is largely based on the spin allowed nature of IC versus the spin forbidden ISC process, as well as the expectation that the surface to surface crossing characteristic of both IC and ISC will be slower than single surface processes such as IVR. So, IVR, this is a process involving only one state, and that's why it is the fastest process. On the other hand, IC and ISC, they are involving two different states, but there is a major difference. IC is involving the same spin state. It doesn't change the spin state. That's why it is faster than ISC. So, this is very well accepted trend in photochemistry and photophysics. In general, the time scale of ISC falls on the order of nanosecond to millisecond. So, this time scale is nanosecond to millisecond. On the other hand, this could be of the order of femtosecond, this could be of the order of femtosecond to picosecond time scale. So, this is the kind of a general trend we have accepted in photochemistry and photophysics. But there is a problem. Ultrafast relaxation of electronically excited inorganic chromophore rubidium bipyridine complex. What is the structure of this complex? I will show you in the next slide. But when the ultrafast spectroscopy was employed to study the relaxation of this complex, with great surprise, it has been found that all the rate constants are competing with each other. In particular, ISC, which is assumed to occur most of the time millisecond to nanosecond time scale. This is the assumption. This is mostly we have seen, but in this complex, this occurs in sub 300 femtosecond time scale, and this is the biggest surprise one can have, and that breaks down the traditional picture of our photochemistry. So, ultrafast relaxation of electronically excited inorganic chromophore revealed a hitherto unknown experimental observation that questioned the validity of the time cascaded model of relaxation stated in the earlier slide, revealing a novel pattern of relaxation of the transition state complexes in which IVR, IC and ISC can kinetically compete with each other, which means their rate constants are comparable. This is not consistent with conventional model for describing photo-induced dynamics in transition metal complexes, suggesting the need to re-evaluate currently accepted views of the excited state behavior of the transition metal complexes. And this was revealed only by ultrafast spectroscopy. For the transition metal complexes, ISC processes may occur in an ultrafast time scale. That's the biggest surprise. For example, In an experimentally well characterized rubidium bipyridine complex, ISC is found to take place in less than 100 femtosecond. This is perhaps the surprisingly fastest ISC ever reported in the literature, and almost with the unity of quantum yield. Therefore, it can be anticipated that triplet excited states have an important role in the photochemistry of this transition metal complex and many other transition metal complexes. This is the structure of the rubidium complex which has been studied, and this is the UV visible absorption spectrum of that complex. The strong visible absorption characteristic of this ruthenium complex is described as an electronic excitation from ground to singlet MLCT state. So, this transition is due to the transition metal to ligand charge transfer. So, from metal centered to the ligand centered charge transfer excitation, in which an electron located in a metal based d orbital is transferred to a pi star orbital of one of the bipyridine ligands. Photoexcitation of ruthenium species to the singlet MLCT state ultimately leads to the formation of a long-lived species in triplet MLCT state. So, what happens once we photoexcite with this photon energy? We excite this system to MLCT, singlet MLCT state, and after this electronic excitation, this system evolves to a triplet MLCT state. So, singlet to triplet transition occurs through intersystem crossing, and the lifetime of this state is already found to be 1 microsecond. That is the lifetime. Femtosecond transient absorption spectroscopy. So, this lifetime of the triplet excited state was known, that is 1 microsecond, but the lifetime of this species was not known, and lifetime or the time scale of this ISC process was not known, and femtosecond spectroscopy was employed to reveal those time scales. For the experiment, a broadband white light pulse is used to probe the transient absorption. That is the way transient absorption spectroscopy is performed. We use white light source, and the white light has a bandwidth 440 to 530 nanometer spectral regime, and that is why we can monitor the absorption in the entire regime. So, this white light broadband spectral width is ranging from 440 nanometer to 530 nanometer, and a short pulse centered at 475 nanometer is used to photoexcite the species to the singlet MLCT transition. So, 475 nanometer was used to excite the species, this ruthenium complex, to the singlet metal to ligand charge transfer state, and then as a function of time, the absorption is monitored. Different absorption spectra in absence of palm pulse different absorption spectra are then recorded in the transient absorption measurements. Excited state difference spectra at various time delays show that the spectral changes in the 440 to 490 nanometer range are quite dramatic. In this regime, the spectral change is quite dramatic. A bleach begins to evolve at 470 nanometer near delta t equals 0. So, this is delta t equals 0, delta tau equals 0, and grows substantially in intensity by delta tau 50 femtosecond. So, by 50 femtosecond it is growing, this bleach signal is growing. The transient exhibits both a marked blue shift and changes in its spectral profile in all of the early time data until delta tau 300 femtosecond. So, it is continuously changing up to 300 femtosecond, and then after 300 femtosecond we do not see any change in the spectrum, and this is continued up to 1 microsecond. There is no change up to 1 microsecond, although 1 microsecond data has not been shown here. Here only 5000 femtosecond we have shown, but if it is continued for 1 microsecond, there is no change of the spectrum. No change in the spectrum until 1 microsecond, it means that we have already created that triplet state, and we know that triplet state exists for 1 microsecond time. This is triplet MLCT. This no change occurs from 300 femtosecond only. So, by 300 femtosecond, the argument from this experiment we can give is that by 300 femtosecond time, we have prepared this 3 MLCT state, this triplet state already, which is long-lived species and it's staying in the triplet state until 1 microsecond time scale. There is no evidence of any additional significant changes in the absorption properties of the complex in the spectra collected from 300 femtosecond to 5 picosecond, and even for 1 microsecond. All of the kinetic and spectroscopic data are therefore consistent with the system being essentially established in the 3 MLCT state in 300 femtosecond, implying a half-life of the formation of the 3 MLCT state on the order of 100 femtosecond. So in brief, what this experimental results suggest that by 300 femtosecond we are preparing a state which remains unchanged until 1 microsecond. This suggests that we have already prepared 3 MLCT state within 300 femtosecond time scale, and half-life if we consider, then is going to be almost 100 femtosecond. So the intersystem crossing time scale is of the order of 100 femtosecond, which prepares this triplet state. Our traditional notions of photochemistry suggest that IVR, IC, ISC can be distinguished from each other based on characteristic time scales. Generally, we have accepted that KIVR is much greater than KIC is much greater than KISC. This is our traditional concept of photochemistry. However, ultrafast study of this ruthenium complex suggests that all these processes can occur in concert with each other. They can be comparable. This represents a significant change in the conventional model for the excited state relaxation processes. This suggests that increased spin orbit coupling due to the presence of the transition metal atoms makes the formerly forbidden singlet triplet transition substantially allowed. Conical intersection between singlet and triplet states can play an important role in the fast ISC processes of transition metal complexes. An important question is still open here. The work presented here shows that S1 to T1 transition is surprisingly ultra-fast. However, T1 to S0 transition is traditionally slow. What does it mean? For this complex, we are seeing that after we excite to the S1 excited state, which is nothing but one metal to ligand charge transfer state, it comes back to the, through ISC, it comes back to the T1 state in 100 femtosecond. But this T1 state, that triplet state, does not decay to S0 state because the lifetime of T1 state is found to be 1 microsecond, which is following traditional photochemistry, but this time scale does not follow traditional photochemistry. Question is why? Why T1 to S0 is slow, but S1 to T1 is very, very fast? Answer, there is no answer found in literature so far, but this is something which tells us that there is a demand for research on it. Our next discussion will revolve around ultrafast relaxation of a biomolecule, which is involved in photochemistry of vision. Many of the sensory information about our world come to us through our eyes. How do we see? What is the initial step of vision? These are the oldest scientific questions which we have asked for a long time. Vision is the result of conversion of light energy to an electrochemical impulse. The impulse is transmitted through neurons to the brain, where signals from all visual receptors are interpreted. Eye vision is initiated when a photon is absorbed by a pigment called rhodopsin. This is the structure of rhodopsin, which is located in the rods of retina. So this back wall is the retina, and in this wall we have a compound called rhodopsin, and this compound is excited to the excited state, and that is the first step of our vision. After optical excitation, this 11 cis retinal prosthetic group of rhodopsin, if you look at the structure of rhodopsin, we see that this moiety is different. This is cis moiety. And what is the difference between photoproduct? The photoproduct is the trans moiety. So what happens after photoexcitation? This 11 cis retinal prosthetic group of rhodopsin is converted to all trans primary photoproduct in an efficient and barrierless isomerization process. This change in shape of retinal apparently gives the signal to opsin to undergo a sequence of dark or thermal reactions involved in triggering neural excitation. So this cis to trans isomerization is the first step of our vision. Photon, the moment we see light, it excites this molecule to the excited state, and that excitation leads to a photoproduct, which is all trans product. Absorption spectra of photointermediates of rhodopsin can help one identify the intermediates very easily. This is the rhodopsin absorption spectrum, and if you look at the other photoproduct, which is this one, let's say all trans photoproduct, it is red shifted. So the peak has moved to the longer wavelength, and that's why we can easily identify what is the product we have formed due to photoexcitation. If the after photoexcitation, if we find that the product is absorbing at 570 nanometer, we confirm that this is all trans product. And if the product is not absorbing at this, if we are seeing absorption at 498 nanometer, it means that we have rhodopsin, which is cis. So this is your cis form and this is the trans form. This difference in absorption spectra can be efficiently utilized in transient absorption spectroscopy to monitor formation dynamics of the photoproduct by recording time evolution of the red-shifted absorption of the photoproduct. So if we see that in the ultrafast spectroscopy, if we see the absorption is moving towards, slowly moving towards the red, then it is what we are observing is the evolution of the cis component to the trans component. Femtosecond transient absorption measurements of the cis trans isomerization of the rhodopsin molecule was explored, and the time scale, the formation time for the rhodopsin protoproduct is found to be 200 femtosecond, which occurs via cis trans isomerization and which is identified as the primary photochemistry of vision. Femtosecond transient absorption spectra of rhodopsin following electronic excitation by 35 femtosecond pulse centered at 500 nanometer. So in this experiment, 500 nanometer has been used as pump, 35 femtosecond, and a broadband 10 femtosecond probe pulse is used to cover the spectral range 490 to 670. This is 490 nanometer to 670 nanometer. At the 33 femtosecond delay time, difference absorption spectrum consists of a very weak absorption between 550 and 620. So in this regime, we have very weak absorption. The photoproduct absorbs in this range. We have seen that photoproduct will absorb in this range, and that's why we are interested in looking at how the change is occurring in this range only, because this is where photoproduct will absorb, and if we keep monitoring as a function of time, we'll be able to get how the photoproducts are formed or how quickly the photoproduct was formed. The absorption of the photoproduct uniformly grows in strength, reaching its largest amplitude by 200 femtoseconds. So if you look at that, by 200 femtoseconds, it has reached the maximum amplitude. It's slowly growing, and it has reached the maximum amplitude. Although the maximum of the photoproduct absorption shifts from 575 to 565 nanometer between 200 femtosecond and 6 picosecond, there is little change in the integrated area or shape of this absorption feature. So what we see that after 200 femtosecond and until 6 picosecond time scale, we do not have much change in the photoproduct absorption. That means photoproduct has been formed within this time scale 200 femtosecond, and then after 200 femtosecond, photoproduct is remaining to be in the same transform. Difference absorbance observed at single probe wavelength 570 nanometer. So when we consider 570 nanometer somewhere here, and we check how the strength is changing as a function of time, that's exactly what is plotted here, the difference absorbance as a function of time. Then we see that 200 femtosecond. By 200 femtosecond, we have created the species already. So the formation time scale of trans is going to be 200 femtosecond. So this all cis product, 11 cis product is converted to trans product in 200 femtosecond, and trans is absorbing in this regime. Measurement of the full difference absorption spectrum of the rhodopsin photoproduct confirms that the first step in vision gets over in only 200 femtosecond. The rapid disappearance of the Frank-Condon excited state absorption near 500 nanometer and rapid appearance of the photoproduct absorption band extending from 530 to 620 nanometer all support the rapidity of the isomerization process. The observation of the cis-trans isomerization of rhodopsin, which is complete in only 200 femtosecond, may have important implications for the photochemistry of vision and photochemistry in general. First of all, 200 femtosecond time is faster than typical vibrational dephasing and vibrational relaxation times, suggesting that photochemistry occurs from a non-stationary vibrational state. This is an important observation because in general when you talk about photochemistry, we show like this way. We have excited the molecule to the excited vibrational states of the upper electronic excited states. They equilibrate and then come back to the lower vibrational state, and then they undergo, let's say, IC, intersystem crossing. But the time scale which is suggested from this experiment, 200 femtosecond, is even faster than this kind of IVR process. And if it is faster than IVR, which means that the relaxation occurs from a non-stationary vibrational state. It is not after equilibrating in the vibrational state in the upper excited state it is relaxing. It is actually relaxing from a non-stationary vibrational state. The equilibrium in the vibrational degrees of freedom in the excited state has not been reached yet before it relaxes back to the ground state. So this is also an important findings revealed by the ultrafast spectroscopy, which also challenges our traditional concept of photochemistry. With this, we have come to the end of the present module. In this module, we have gone over two interesting examples. One example is based on transition metal complex, and another example is based on a biomolecule. In both examples, we have found that ultrafast spectroscopy has revealed few information which can challenge our traditional concept of photochemistry and photophysics. We'll meet again for the next module.